Atmospheric methane, since it's a potent greenhouse gas, it accounts for 30% of the climate warming that we are experiencing today. And methane is also a precursor for tropospheric ozone, which is harmful for air quality. So methane indirectly also affects air quality in addition to these major climate warming implications. So reducing methane can benefit our long-term climate, but also air quality.
Hi, I'm Stephanie Tumampos, and you're listening to Down to Earth, the show where we talk to incredible geoscientists about their science and its impacts on our planet. This season, we're exploring stories of resilience, hope, and scientific insight into climate change. As a gas that has more than 80 times the warming power of carbon dioxide over a 20-year period, methane is a major contributor to global warming. But the good news is, unlike CO2, methane has a very short atmospheric lifespan, around 10 years to be exact. According to the United Nations Environment Program, by cutting human-caused methane emissions by 45% within the decade, we would avert nearly 0.3 degrees Celsius of global warming by 2045. This reduction would help us get back on track for our Paris Agreement target of limiting global temperature rise to 1.5 degrees Celsius. Today, we look at how we can reduce our methane emissions through the use of satellite technologies. We also learn about an exciting new satellite mission being launched for this very purpose in 2024. This episode of Down to Earth is brought to you by the Remote Sensing Environment Analysis and Climate Technologies, or REACT Technical Committee, of the IEEE Geoscience and Remote Sensing Society. The REACT Technical Committee is a collaborative and supportive venue for all scientists and engineers looking to exchange ideas and share knowledge that advances our efforts to tackle climate change. To learn more and be part of this incredible cutting-edge community, visit grss-ieee.org and select the REACT Technical Committee.
So aerosols come in different shapes, colors, sizes, properties. They come from different points of origin, sources of origin. They're natural, they're human-made. And it doesn't really matter where the aerosol or pollution is being originated from. It gets to impact all around the world and the people living in densely populated places.
This is Dr. Ritesh Gautam, lead senior scientist with Environmental Defense Fund, or EDF for short. He's an atmospheric scientist who is super passionate about understanding and mitigating the impacts of air pollution on climate and society.
So I started my sort of research with the aerosols and air pollution. My basic training and background and research experiences in atmospheric science and satellite remote sensing. So I work on mapping and quantifying air pollution from satellite remote sensing observations all over the globe. But at EDF, I've been mostly working on methane pollution and methane emissions. And I've been with EDF for 6.5 years.
At EDF, Ritesh is involved in environmental data creation and data analytics from a range of satellite missions. With this information, he helps to deliver actionable products and scientific insights for informing strategies on pollution mitigation. One of his main projects has been a brand new satellite mission focused on methane that's set to be launched in early 2024. Let's learn more. Before we jump into specifics on methane, I want to talk about aerosols in general. So what are we talking about when we say aerosols? Can you give some examples?
So there's dust storms that are part of the natural aerosol system. Then there's volcanic ash that can get injected high into the atmosphere, actually into the stratosphere even. And then there are very prominent examples of urban air pollution or urban sources of aerosols. So for example, power plants, industry, vehicles that are producing these different types of aerosol particles that are actually very bad for your health. So they also impact the air quality and the visibility. So there are these different types of aerosols, which I just described, natural and anthropogenic, human-made. And each of these aerosols have different properties, so they can affect the climate in different ways.
How so? Can you give a specific example?
Yeah. For example, some of the highly absorbing aerosol types, such as soot particles, can absorb the incoming sunlight. And then as a result, they can warm the atmosphere and at the same time cool the ground surface. So they cause a dimming effect at the ground surface while warming the atmosphere. And as a result, that tends to create some energy imbalance within our Earth atmosphere system, which can drive down lots of changes in the heating patterns, the cooling patterns across the Earth. It can affect rainfall processes, and then cloud properties can get modified as a result of how these aerosols interact with different types of clouds. The other significant impact of aerosols that have come very prominent in the last few decades is once these aerosols are deposited on snowpack. For example, black carbon or soot particles get deposited on snow and glaciers, and they can darken the bright snowpack. And as a result, they can reduce the albedo of the snow or the brightness of the snow. So basically, the snowpack or the glacier will start to absorb significantly more solar radiation, incoming sunlight. And then you can expect more or accelerated snow melt happening. So these are some of the effects that motivates us to look into this aspect of aerosols. And one of the best things about satellite remote sensing is that we can monitor these air pollution and their trajectories and pathways all around the world without having any sort of physical boundaries.
That's really interesting, Ritesh. I think when people talk about air pollution or aerosols, they're thinking about the impact on human health. But you mentioned that aerosols contribute to melting snowpack, change rainfall patterns and cloud properties, and of course, warm the atmosphere. So aerosols aren't just impacting people, they're also changing our environment. So today's episode is focusing on methane in particular. Can you define methane for us? How is it formed and what role does it play in climate change?
Right. Methane is a greenhouse gas, and atmospheric methane accounts for 30% of the climate warming that we are experiencing today. So that's pretty significant, right? Because methane stays in the atmosphere for about 10 years. So if you reduce the amount of methane today, you will start to see near-term climate benefits in about a decade from now, which is in sort of contrast with CO2, because CO2 lasts in the atmosphere for centuries. So in order to really see those climate change benefits, we'll have to wait for many, many decades, if not even centuries. But we have to focus on both methane and CO2. So methane in the Earth system is produced from geological and biological processes. So there are very prominent and large natural sources of methane. For example, methane from wetlands. And there are very, very prominent and increasing sources of anthropogenic methane, agriculture, landfills, oil and gas systems. So that's been undoubtedly a very steep increase in methane emissions and concentrations that we are seeing in the last many, many decades that are linked to anthropogenic emissions.
And what are we seeing so far in terms of methane release rates?
Right. So again, there are different types of sources of methane. And in terms of the emission rates or the release rates, there are some prominent sources. For example, the oil and gas infrastructure system, which is responsible for these sometimes very large leaks that we can observe even from satellites, but also very small, fine pointed leaks, which are often not detected in routine measurements. And because of these leaks that are not being detected or reported, they're often missing from the methane budgets that are being developed by the industry and by governments and by sort of climate coalitions. So the real challenge is to map and quantify the different types and the different sources of methane leaks or emissions that are happening all across the world, from not just from the oil and gas sector, but also from a number of other sectors, including agriculture and landfills. In terms of the release rates, they can vary. They can sometimes be of the order of just a few kilograms per hour, but we have also seen some massive release rates coming from landfills or large upsets in the oil and gas infrastructure, single point failures such as blowouts that could release many, many hundreds, even thousands of kilograms of methane per hour. So that's really very dangerous levels of methane that can be released to the atmosphere. And if they're getting released at that rate, sustained over long periods of time, they can result into very large amounts of methane emissions.
And you mentioned earlier that satellite remote sensing allows us to monitor aerosols globally. So, what technologies are we using to monitor methane? Can you give us a bit of history here?
Yeah, that's a great question. So, methane remote sensing from space started almost 2 decades ago. And it sort of all started by the Skamaki satellite that was launched by the European Space Agency. And observations made by that satellite really enabled the science community and the remote sensing community to develop new algorithms to process and analyze methane remote sensing observations from satellites. The Skamaki satellite was global in scope, so it also provided data at the global scale, but it was limited in a way that the spatial resolution or the granularity with which we can attribute sources was pretty limited because of the very coarse spatial resolution. Since Skamaki, there have been other satellite technologies and platforms that have been launched by other government-led space agency programs, such as the GoSat satellite that was launched by the Japanese aerospace organization in the late 2000s. Since then, we have had the Tropomi satellite that was launched in 2017, again by the European Space Agency, that has been really successful in providing global access to methane concentrations data. But these satellite observations, led by the government-led space agencies, provide highly relevant science data. But the science data in terms of the methane concentrations are not necessarily always actionable in terms of policy, because they don't directly provide data on methane emissions on the ground, which is what the policy makers, the stakeholders coming from industry or from regulatory bodies need, because that's what you want to measure and mitigate. So there have been some initiatives also from the commercial sector in recent years that have launched satellites that are sort of directly measuring emissions from individual facilities in a limited way. So there's a commercial company called GHGSat, which operates out of Canada, which has launched a number of high-resolution satellites that are focused on pinpointing individual methane plumes from facilities. But there is still a major gap that exists between these global scales and the facility scale. So that gap still persists in the current ecosystem of satellites, and a number of other satellites that are coming online in the next couple of years, including one by our organization, EDF, which is launching Methane Sat to map and quantify emissions from area sources, in addition to these high emission point sources that some of the existing satellites detect.
MethaneSat is a unique satellite because it's the first time in history that an environmental group is launching a space mission. What will MethaneSat do that other governmental and commercial satellites don't? And how will MethaneSat help EDF achieve a 30% reduction of the 2020 global energy and agricultural methane emission levels by 2030? We'll find out right after the break.
Are you passionate about protecting our planet and tackling the challenges posed by climate change? Do you want to be a part of a remote sensing community that brings together the brightest minds in environmental science and engineering? Then you need to check out the Remote Sensing Environment Analysis and Climate Technologies Technical Committee, or REACT-TC for short. Here on the REACT Technical Committee, we believe strongly that interdisciplinary collaboration is key to making a real difference in our world. That's why we bring together experts from various fields to exchange ideas, share knowledge, and advance the science that drives our understanding of the planet. Whether you're a scientist, engineer, or simply someone who cares deeply about the environment, the REACT Technical Committee of the IEEE Geoscience and Remote Sensing Society is a place for you. Together, we can make a difference, one discovery at a time. Visit grss-ieee.org and select the REACT Technical Committee to learn more.
Welcome back. Today we're speaking to Dr. Ritesh Gautam, lead senior scientist with Environmental Defense Fund, or EDF for short. Ritesh is an expert in aerosol and pollutant monitoring using satellites, and he has applied this expertise at EDF towards an exciting new project focused on methane monitoring, MethaneSat. Scheduled to launch in early 2024, MethaneSat is the first satellite to be launched by an environmental group, and it is proposed to be the most advanced methane tracking satellite in space, capable of measuring methane emissions pretty much anywhere on Earth. The main goal of this project is action-oriented. EDF wants to ensure decision makers have the information necessary to quickly respond to methane leaks, primarily in the oil and gas sector. The oil and gas industry is the second largest source of human-caused methane emissions, releasing around 80 million tons of methane into our atmosphere every year. MethaneSat data will not only allow countries and companies to prioritize methane emission reductions, but by providing the satellite data openly and for free, MethaneSat will make it faster and cheaper to locate, measure, and reduce oil and gas emissions globally. Let's find out how this ambitious project came to fruition, and where Ritesh and the EDF team hope it will lead. So tell us about the MethaneSat mission and the tech that will be used.
So MethaneSat was conceptualized in 2015, and then it was publicly announced in a TED Talk, actually, by EDF President Fred Krupp in April 2018. Since then, we are aiming for launch in early 2024, and the satellite will be launched by SpaceX. We have science teams that are being led by Environmental Defense Fund. We have science teams also at Harvard University and other institutions that are supporting this development of MethaneSat. In terms of the instrument itself, the instrument is being developed at Ball Aerospace, and EDF is managing and leading this whole mission. And one of the main mission objectives, which was built into the mission at the time of conceptualizing this mission, was not to only detect and sort of characterize the concentrations of atmospheric methane, which is a highly useful scientific quantity, but also more importantly, retrieve the amount of methane emissions that are happening on the ground, which can be directly used for policy interventions and for tracking the emission targets.
So, why is it significant that this is the first ever environmental group to launch a space mission? And just to add on it, what makes it different from the other technologies before?
Yeah, that's a great question. And it's most probably never been done before in terms of launching a satellite from a nonprofit environmental group. So it is very ambitious. Typically, the satellites that have been launched in the past for methane remote sensing have been launched by the government-led space agencies like the European Space Agency, the JAXA by Japan, NASA in the US. And they have produced very useful data, but that data is limited to methane concentrations. That doesn't directly tell us how much emissions are happening on the ground. And some of these data sets are also limited in terms of the level of source attribution that you can do in terms of identifying and pinpointing where the emissions are coming from. There has been a growing need in the methane remote sensing community, not just from a science perspective, but also from a policy perspective, about the granularity of data that is needed, not just in terms of concentration, but most importantly in terms of emissions. So how much emissions can we quantify? How much emissions can be attributed to different types of sources? How much emissions can be quantified in terms of how much oil and gas is being produced from a field level or from a basin level? So all of this information is really lacking across the globe. So EDF came up with this idea or this concept of really going after emissions and not necessarily after concentrations. And that's how MethaneSat was conceptualized. The significant part of this technology is that it's a unique combination of three different types of specifications sort of built into a single form factor, which is high precision. So we will be able to detect methane concentrations in the atmosphere. Our goal is to detect them at 3 to 4 parts per billion, which is really significant because if you stick out an instrument and if you measure the amount of methane concentrations in the atmosphere, you will get readings of what we would routinely detect as somewhere around 1900 parts per billion. So 3 over 1900 parts per billion means less than 0.2% of precision. So that's the level of precision. that is being built into this imaging spectrometer that will be launched on the satellite, on the methane satellite, that will be used to map and quantify emissions. So that's one. And then methane sat will have a large width of swath that will allow us to map wide areas all around the world. So methane sat will have a swath of about 200 kilometer, which can be used to map an entire oil and gas field or a basin or an agriculture field. So it's not just looking at smaller or individual facilities, but a collection of facilities, which could be in the hundreds or thousands within an individual oil and gas field or agriculture area. And the third is the resolution. So it's very high resolution. So our native pixel resolution is around 100 meters by 400 meters. We will be able to attribute individual methane point sources or area sources at very high resolution. So it's a unique combination of three specifications, like I said: the precision, the broad swath width, and the high spatial resolution built into one sort of system. And then on top of it, our main mission objective is to map and quantify emissions. So there is an operational data processing pipeline that is being developed and finalized for this mission, which will allow the routine production of methane emissions data from the raw data that is being collected. So we won't be limited to the methane concentrations level, but we will go up to the level, what is called the level 4 methane fluxes, or the amount of emissions that are happening on the ground. We will be able to track those emissions over time, and we'll track the progress of the pledges and the commitments that are being made by countries and companies around the world to reduce methane emissions.
Exciting times ahead. That's really a really good mission that I think a lot of researchers are excited about. So, Ritesh, in past episodes, we've spoken to scientists who work in the private sector and use satellites to study the planet. And we always hear from these folks about the last mile that is sometimes missed in research focused missions. So, meaning the policy change connection isn't always there. So, since the Environmental Defense Fund is nonprofit, are they highly focused on the policy and practice change component of the mission? What specific goals are they hoping to achieve?
Right. So at Environmental Defense, we are really guided by science. All of our work is strongly grounded in good science and strong, robust science. But we are also producing science that is relevant to policy and how it can inform or shape policy making in order to reduce emissions. In a similar fashion, Methane Sat was developed, where the main mission objective is to map and quantify methane emissions. And we ultimately want to see reductions in emissions. So stakeholders such as industry or regulatory bodies will be able to directly sort of ingest this methane emissions data in order to track their progress, in order to track the reduction in emissions that are happening from their facilities or from their operations, from a field level, but also at a large area level, at a state level or at a basin level. Methane sat data will also be contributed to recent programs such as the IMEO, which is the International Methane Emissions Observatory, which has been started by the UNEP. The main goal for the IMEO is to build a transparent data hub of different sources of methane emissions, whether it's coming from satellite observations or from company reports or from government reports. So Methane Sat will provide this data to IMEO, and Methane Sat will make all of the data available for free in the public domain. So that will enhance the transparency associated with this mission and the data that is being produced.
So, you mentioned that MethaneSat will be able to help us track government and private sector commitments to emission reduction. Talk to us about these reduction pledges. What targets are we aiming for, and what do we still need in order to encourage these entities to meet their targets?
So, for example, the Global Methane Pledge was announced a couple of years ago at the COP26. And now there are more than 120 countries that have signed on to the Global Methane Pledge. And one of the main targets for the Global Methane Pledge is to reduce anthropogenic methane emissions by 30% by year 2030. So that's one sort of very, very prominent and a positive emission target that has been announced. Similarly, oil and gas companies, several oil and gas companies have pledged to reduce their methane emissions down to 0.2% of production. So that's another very ambitious industry target that's being pledged. And some of the companies and some of the governments all around the world are already working towards reducing these emissions. But we have a lot of work to actually measure them and track them. And that's where these disparate remote sensing or ground-based or other aerial technologies are being deployed to measure these emissions and to really track them over time.
How do we actually reduce methane release? Like you mentioned, oil and gas companies have pledged to reduce their methane emissions down to 0.2%. That's ambitious. So, can you give us an example of how an oil company might do that?
So, in the oil and gas sector, there are different types of leaks happening. There are different emission scenarios, there are different emission profiles, right from few grams or few kilograms per hour to hundreds of tons per hour. And the oil and gas infrastructure is very complex and quite dispersed, at least in the US. In some of the international geographies, it's a lot more concentrated, but that poses its own complexity. So there are a number of different pathways that emissions are being, that these leaks are happening and the emissions are being put out to the atmosphere. There is venting happening, there's flaring happening, and the flaring that happens from the oil and gas infrastructure sometimes happens at very inefficient flaring rates. There is evidence where there is actually an unlit flare going on, which effectively puts out all of the methane without being burnt directly into the atmosphere. So that's really very inefficient way of flaring gas, which can be directly addressed by putting practices and infrastructure to make the flaring process highly efficient. Other areas of intervention, technological and policy-wise, are gas capturing and processing. Capturing the gas effectively where it is being produced and processing it on the same site can often reduce the amount of methane emission that instead will be put out to the atmosphere. And then similarly, improving infrastructure related to transport and pipeline takeaway capacity can also reduce the amount of methane emissions that are happening. There are leak detect and repair programs that the industry and the governments have been investing in. But to be able to really achieve these measures at scale, you also need data on how much methane emission is happening. So we don't have a really quantitative understanding of how much methane emissions are happening across the global oil and gas supply chain, which is why satellites are so useful and really relevant.
Mm-hmm. Okay. So, in your view, Ritesh, what are the next steps for research and monitoring of methane?
So, in terms of monitoring, there is a clear need for mapping emissions, but also attributing these emissions at very fine scales. Because we often find in areas that are releasing methane that there could be multiple sources leading to anomalous methane emissions. So there can be an oil and gas field, but within that oil and gas field or basin, there can be an agriculture field right next to it, or within that footprint, there could be a feedlot with high density of cattle that could be also releasing or emitting methane. So how do you disentangle sources? Because unless we really link these individual sources to the amount of methane emissions, unless we build a very highly granular inventory of methane emission sources, we cannot really devise effective mitigation strategies.
So that makes sense. What keeps you positive about your work in light of climate change? Are there any policy changes, projects, or activities that are keeping you inspired and hopeful?
Yes, with the increasing technology and the deployment of more sort of sensors and more satellites, we can really track the changes over time, hopefully the reduction in emissions over time. That makes us very optimistic about the role of technology in reducing emissions, but data doesn't necessarily lead directly to action. And I think that's where the unique role of organizations like EDF or other nonprofits come into play, where we can build very transformative campaigns to put these data into practice of motivating global action to reducing emissions.
So, what's one concrete action you think listeners could do in their own lives, either as researchers or as citizens, to address the challenges surrounding methane release into our atmosphere?
So, from a research perspective, I think we need to create an even better understanding of methane emissions, their sources, the magnitudes of the emission rates, where they're coming from. I think we also need to work on better identifying or distinguishing what data are empirical and what data are based on measurements versus which data are less empirical or are only based on engineering estimates that are not necessarily supported by measurements. Because often there's a difference or a discrepancy in the information on methane emissions. So how can we bring these different types of estimates together and build a more complete story of emissions? I think the scientific community and the policy community needs to work even more closely together on better understanding and distinguishing these differences and reconciling them. I think as public, as citizens, we can better manage our sort of environmental impact. We need to be sort of more conscious of our choices. For example, landfills is an example where the human waste that is being produced outside of our houses or just our daily habits is being dumped into a landfill. And over time, that landfill is undergoing anaerobic decomposition of organic matter, which leads to methane emissions. So that's happening all around the world. So I think that's a direct sort of intervention that a normal citizen can undertake, where you're more mindful of your practices of generating waste.
Well, that's all for this episode of Down to Earth. Want to learn more about Dr. Ritesh Gautam's work with MethaneSat and Environmental Defense Fund?
We have a website, MethaneSat, so the developments that are happening related to MethaneSat are available on the website. We have a Twitter handle. We also have a LinkedIn page for MethaneSat. Similarly, EDF has a very active Twitter handle where we are posting updates on all of the latest that is happening with methane, MethaneSat, and other areas that EDF works on.
Be sure to rate and follow us on Spotify and Apple Podcasts, and share your feedback on our episodes so far. Also check out our sponsors at IEEE_GRSS on Twitter and Instagram, and IEEE Geoscience and Remote Sensing on Facebook and LinkedIn. This episode was produced by Nicole Bedford from Nicole Bedford Films, with help from me, Stephanie Tumampos. Graphics and design by Mylene Briggs of Kila Media. And a special thanks to Irina Hansek of ETH Zurich and the German Aerospace Center for her support. I'm Stephanie Tumampos, and you've been listening to Down to Earth.